K8BYP with the 7th video in the series of chasing after the ultimate balanced modulator / mixer for the Drake TR3. Put the new and improved circuit in, perfectly balanced, should not need any adjustment, and there's still a spurious carrier at the final grids. Also, when listening to the local receiver, there's a noticeable AC hum, which is not good in my opinion. I've never gotten reports of AC hum on a signal from this radio, but it is there. The carrier signal is about 2.2 volts peak to peak, nice and flat across the top. From the balanced modulator transformer, looking at the RF cycles, it's basically a sine wave. The positive peaks look good on one side of the transformer, the negative look terrible, folded up something. I don't know what's causing that, but it looks somewhat like that. So at low sweep rates, it looks like there's kind of a line through the bottom of the wave shape. On the 250 volt power supply, there's 120 cycle, half cycle, positive going ripple, 1.2 volts. That shouldn't make much difference out of 120 volts, except that supply does not, that supply feeds the carrier oscillator through substantial filtering. That supply is dropped down to 230 something with more capacitance, and that knocks out the ripple. And the balanced modulator is not powered. It's powered by the carrier signal, so interference can't get into it. But the mixer and the final driver stage have that ripple on their plates, and that's causing a lot of AM modulation in the mixer output, and relatively speaking, severe distortion of the carrier wave at the final grid input. Not acceptable. Receiver performance isn't of much importance to FCC, but we're required to have good, clean signals in amateur radio. We're supposed to know how to find problems like this and fix them. This is not CB radio where we can just say, oh, that's good enough, and ignore it. The power supply had the dropping resistor there, 5-watt resistor, too close to one of these capacitors. It badly overheated the capacitor, so I replaced all three. The underlying question with transformer power supplies was shown in a previous video about power supply, where I measured the AC voltage between the TR3 chassis and the oscilloscope at about 30 volts. But when I reversed the AC line plug on a Drake TR3, that potential dropped down to about 2. So a massive drop in leakage current. That's good. There's a thing with transformers called phasing. There are no phasing dots or marks usually on a simple power transformer, but there's always leakage, and power transformers are not isolation transformers and not specifically designed to minimize leakage. Particularly in RF transformers, this is a schematic maybe for a power transformer, but assume the top 2 windings only. An RF transformer might be dotted. You may see phasing dots on a schematic, and might literally see on a transformer can phasing dots painted on the base to indicate which lead is which. Those phasing dots indicate arrangement of the windings with regard to each other and perhaps with the core. And what's important is to understand that there are leakage paths, literally for magnetic flux and current, from the primary to the secondaries through the core and also among the secondaries. And it may be helpful, especially in applications that need to be very clean, to phase these leads. So that, for example, the top 2 secondary windings here, imagine a voltage from dotted leg to dotted leg. That might be minimal towards 0. But the phasing, the voltage, the leakage paths potentials from the top dotted leg to the bottom winding that's inverted top to bottom might be a much higher potential. Now realize that, especially if there's a circuit out past those secondary windings through diode and capacitor power supplies, that those potentials are still across that power supply, and when those windings are coupled together by a circuit somewhere else, there then could be leakage passed through those circuits, and I suspect that's what's happening here. So if there are no phasing dots or marks, what to do? Well, get a variac and put a small AC potential on the primary and use an oscilloscope to measure across the secondary leads. For this power supply, for the 250 volt supply in the Drake TR3, it's the 2 yellow leads, 2 red for the high voltage, blues for the minus 65. But do it on a variac, less chance of getting shocked, less chance of excess leakage current through the scope, and just measure the pairs of leads from the windings and determine which orientation of the scope has for example, a positive going half cycle with the oscilloscope probe on the top wire and the ground on the bottom wire compared to the primary. A little difficult to explain, but you'll see it if you try it. Especially if the secondary windings are grounded. But see which orientation of the scope probe and ground clip results in a positive going half cycle compared to the primary, and then mark that lead as dotted, and do that for all the leads. And that may make a substantial drop in AC ripple. And this ripple on this 250 volt supply could not be filtered out. I added significant filter capacitance in the rig, didn't do anything. So that suggests maybe it's either leakage, or maybe because a 250 volt supply is a voltage doubler, maybe the 250 volt secondary center tap is out of balance by a shorted turn, maybe. Or maybe it just wasn't wound as precisely as maybe it could be. That's not repairable without taking the transformer apart, and I'm not going to do that. So the next video will be hopefully with this ripple resolved and back on a trail of figuring out why the mouse modulator is off just a touch. KBYP.